So, warm welcome to the 38th lecture on the subject of digital signal processing and its applications. We proceed in this lecture to build a few more approaches to efficient implementation of the discrete Fourier transform. Let us recall what we did in the previous lecture. We had seen some variants of the fast Fourier transform or FFT algorithms only for powers of 2, number of points equal to a power of 2. Now there again we had decimated, so to speak, in time and in frequency, and we had looked at the decimation in time approach in detail, and we had put down the approach, the main idea behind the approach for decimation in frequency. And we kind of conjectured, or we just stated directly, that if you look at the signal flow graph for decimation in frequency, it would be the transpose of what you get with decimation in time. What it means is there is a close relationship between them, and in fact the computational complexity is the same, but there could be other reasons to choose one for the other. Now today what we wish to do is to generalize the fast Fourier transform approach when the number of points is a composite number, not necessarily a power of 2. In fact, we shall evolve a general approach for a composite number which can then be used recursively, as we did actually in the power of 2 case. So if you have a composite number, you could break it up into two not necessarily prime numbers again. It could be broken up into two factors which are themselves composite possibly, and you could then implement a discrete Fourier transform of the composite number of points in terms of discrete Fourier transforms involving the smaller number of points and combine them using some additional computation. Now the secret of efficiency here is that what remains ultimately is just small size discrete Fourier transforms together with some additional computation, and that in general is more efficient, or that in general is more efficient than using a large size discrete Fourier transform. That is the central idea. Okay. So let us formulate the approach in detail and in depth. Let us consider a composite number capital N given as a product of M and L. Now M and L need not be prime. They could, of course, but they need not be prime. Could themselves be composite. So to take examples of both cases, if n is equal to 15, then you have n equal to 3 into 5 or n equal to 5 into 3, both of which have their own meanings, and here both are prime. On the other hand, you could have n equal to 8, in which case n can be decomposed as 2 into 4 or as 4 into 2. Here 2 is prime, 4 is composite. And finally, of course, you could have n equal to 16, in which case n could be decomposed as 4 into 4 or as 2 into 8, in which case here you have a product of two composite numbers and one prime and one composite here. So all these possibilities are accepted. So in general, if we decompose n equal to m times L, then we can write the discrete Fourier transform with m points as follows. Capital X of k is summation n going from 0 to capital N minus 1 x n e raised to the power minus j 2 pi by n times n k. And the secret of efficiency here again is to decompose n and k with different factors. So you have chosen n equal to ml and you decompose n as n times n1 plus n2, where n2 must of course go from 0 to n minus 1 and n1 must of course run from 0 to L minus 1. So to take an example, if you take capital N equal to 15 here, you are saying that you write n, so 15 can be decomposed in two ways. So suppose, let's take an example, let's write down the example clearly. N equal to 15, so small n goes from 0 to 14. And therefore n can be written, and you can write it as 3 times 5. So m is 3 and L is 5. In which case I am writing n is 3 times n1 plus n2, whereupon n2 goes from 0 to 4 and n1 goes, n2 goes from 0 to 2 and n1 goes from 0 to 4. So essentially the maximum number which you would have here is 3 times 4, that's 12, plus 2, that's 14, that as expected. Now in contrast, we decompose k not using m but using L. K is written as L times k1 plus k2, and of course k2 would naturally run from 0 to L minus 1 and k1 from 0 to m minus 1. So here for example, k would go from 0 to 14 in this example where capital N is 15, k2 would run from 0 to 4 and k1 from 0 to 2. You are saying essentially k is of the form 5k1 plus k2 here. So as you can see, we can always decompose or we can rewrite the index n and the index k in terms of the double indices n1, n2 and k1, k2 in this way, whatever be the decomposition. What is to be noted is that the decomposition of n is complementary to the decomposition of k, while n is decomposed modulo capital M, k is decomposed modulo capital L. Now with this, we write down the discrete Fourier transform once again. So we write x L k1 plus k2 is summation n2 going from 0 to m minus 1, summation n1 going from 0 to L minus 1. Now I continue on the next line, x m n1 plus n2 times e raised to the power minus j 2 pi by ml times m n1 plus n2 into L k1 plus k2. So we write it all in terms of k1, k2, n1 and n2. Now our whole attention is on this factor. Our whole attention will now be on this factor, on the factor e raised to the power, the exponential factor. So let us simplify or decompose the exponential factor. First, let's expand the product. So 2 pi by ml m n1 plus n2 into L k1 plus k2 is 2 pi by ml into ml n1 k1 plus L n2 k1 plus m n1 k2 plus n2 k2, and that can be written as 2 pi n1 k1 plus 2 pi by m n2 k1 plus 2 pi by L n1 k2, and finally 2 pi by ml n2 k2. And we substitute this expansion back in the exponential. We need to raise this expansion to e raised to the power minus j times. So what we want is really e raised to the power minus j times this. Thus, e raised to the power minus j times 2 pi by ml into m n1 plus n2 into L k1 plus k2 becomes, now let's look at each factor in turn. See, it's essentially when you have a sum of terms and you take an exponential, it's going to become a product of the corresponding factors. Now, e raised to the power minus j 2 pi n1 k1 is just 1. This is a multiple of 2 pi, so it doesn't need to be written at all. The other three factors need to be written. So it's a product of three factors. E raised to the power minus j 2 pi by m into n2 k1 e raised to the power minus j 2 pi by L into n1 k2 into e raised to the power minus j 2 pi by ml n2 k2. And therefore we can now rewrite the summation that we had using these three factors. Moreover, we see that we have two summations or two terms involving n2 and only one term involving n1, and now n1 and n2 have got decoupled, and in fact in some sense so have k1 and k2. So this term involves k2 but this one does not. So let us take this term right inside. So let us write down the discrete Fourier transform as follows. Thus the endpoint discrete Fourier transform becomes xl k1 plus k2 is, now we will take the summation of n1 outside. 0 to L minus 1. I am sorry, summation on n, well, let us write it down, let us complete the multiplied by e raised to the power minus j 2 pi by n n2 k1. Let us write the factors with n2 together. So what I am saying is that the summation on n1 will act only on this and this. So we can take the summation on n1 inside. And therefore rewrite this as x L k1 plus k2 is summation on n2 outside. Now this is multiplied by e raised to the power minus j 2 pi by ml n2 k2 times summation on n1 going from 0 to L minus 1 x m n1 plus n2 times e raised to the power minus j 2 pi by L n1 k2. And now we pay careful attention to this term here. In this term, n2 is fixed. So we are taking all the n1s, the L values of n1 for a given n2. And this is essentially an n-point discrete Fourier transform of those points. It's an n-point discrete Fourier transform. And whenever you have a discrete Fourier transform, there is a corresponding frequency index. So here the frequency index is k2. And as expected, k2 takes the values 0 to L minus 1. That is to be expected. You are taking an n-point discrete Fourier transform of x m n1 plus n2, n1 running over L samples for each n2. So you have for each n, you see n2 takes capital N values. So for each n2 you have one L-point discrete Fourier transform, and the index, the frequency index of the discrete Fourier transform is k2. Now liken it to the case of decimation in time. There what you did was to decimate in time. Now there you had chosen m equal to 2. So essentially you had two discrete Fourier transforms of size n by 2. You see, you had two discrete Fourier transforms of size n by 2 there. And they were of course indexed by their respective frequency indices, and then this is what you did to carry out additional computation. Now note that the output is indexed by n2 and by k2. n1 has been summed out, n1 has gone in the summation. So this is a function of n2 and k2, and for each n2 and for each k2 you have a different multiplying factor here. So you are calculating a set of discrete Fourier transforms, and each output of the discrete Fourier transform is multiplied by a unique multiplier here. Needless to say, some of these multipliers are trivial. For example, when n2 is equal to 0 or k2 is equal to 0, the multiplier is trivial. And in some cases where you are fortunate to get this equal to minus 1, also the multiplier could be trivial. Otherwise, these are non-trivial multipliers. And naturally, you have a multiplier for each value of n2 and for each value of k2, and there are n possible values of n2 and capital L possible values of k2. So therefore, in general, you have m times L multipliers when counted crudely, but some of them are lost on account of becoming trivial. So you see, having done this, what are we doing next? So let's give this a name. We note that summation n1 going from 0 to L minus 1 x m n1 plus n2 e raised to the power minus j 2 pi by L times n1 k2 is the L point discrete Fourier transform of x m times n1 plus n2, n1 going from 0 to L minus 1 for each n2, and the frequency index is k2. As expected, k2 also takes values from 0 to L minus 1. Let us denote that particular quantity by x tilde. Let us denote it by x tilde as a function of n2 and k2. For each n2 you have one such, and the frequency index is k2. So what we have next, the next step is pointwise multiplication. X tilde n2 k2 multiplied by e raised to the power minus j 2 pi by ml n2 k2. So pointwise multiplication. And let us denote this again by a different symbol. X double tilde now look back at the summation. We've taken care of this, we've taken care of this. Now this whole curly bracket expression is x double tilde. Now x double tilde is acted upon by summation m2 going from 0 to m minus 1 e raised to the power minus j 2 pi by m, this time 2 pi by m, n2 k1. So it's very clear that this is essentially, for every value of k2, it is an m point discrete Fourier transform. So we have capital X, the final capital X, L k1 plus k2 is summation n2 going from 0 to m minus 1 x double tilde n2 k2 e raised to the power minus j 2 pi by n times n2 k1. So, this is an n point discrete Fourier transform of x double tilde n2 k2, n2 as expected running from 0 to n minus 1 for each k2, and the frequency index is now k1. Of course, k2 was also a frequency index. So, when we reached k2, we had partly moved into the frequency domain. Now, we have completely moved into the frequency domain. Now, let us get our ideas very clear by again using a particular decomposition of n equal to 15, and then we will see what we are doing, and we will also see the case of n equal to 8. Now, in fact, you see, let us take n equal to 15 for variety, otherwise you have done n equal to 8 before. And let us decompose this into m in m cross L, or m multiplied by L, where m is 3 and L is 5. So, what is the situation now? You see, at first we took, let's draw this whole situation pictorially. We first take an L point, L means 5. A 5-point discrete Fourier transform of x m n1 plus n2 for each n2. So, you know, x here it will be x 3 times n1 plus n2, and you see you have a 5-point discrete Fourier transform. So, as expected, n1 goes from 0 to 4, and for each n2, n2 would run from 0 to 2. So, what is the situation? We first take 5-point DFTs of x 3 n1 plus n2, n2 going from 0 to 2 for each n2, time index is n1 going from 0 to 4 as expected. Let us draw this structure. So, you see, we have, remember, we have to aggregate corresponding to n2. So, let us form one group with n2 equal to 0, the next group equal to n2 equal to, for n2 equal to 1, and the next group with n2 equal to 2. So, the groups are going to look like this. We are going to have x0, x3, this is for n2 equal to 0, x6, x9 and x12. Then you are going to have x1, x4, 7, 10 and 13, and this is going to be the group corresponding to n2 equal to 1, and of course the output index is going to be k1, I am sorry, k2, the output index is k2. So, you see, you can think of a 5-point DFT box here. You can think of a module which computes a 5-point discrete Fourier transform. And the input pins of this box are indexed by N1. So N1 takes the value 0, 1, 2, 3, 4. And the output pins are indexed by K2. As expected, K2 also takes the value 0, 1, 2, 3, 4. So every pin here on the output box, on the output, has an identifier with N2 and K2. There is a 2-index identifier. Each pin here has a 2-index identifier, an identifier which has N2 and K2. In fact, you get the X tildes here, X tilde N2 K2 here. So of course a similar thing can be done for the third group of 5. So X2, X5, 8, 11 and 14. That also gives you 5 outputs. This is N2 equal to 2 and you have a 5-point DFT. So it is very clear that each of these pins here give you a unique X tilde N2 K2. Is that clear? Now, therefore, each of the pins must now be attached to a multiplier. Each pin, each output pin, X tilde N2 K2 carries a multiplier, carries a corresponding multiplier. E raised to the power minus j 2 pi by ml N2 K2. Now we need to appreciate this. We must take specific values and appreciate what's going on here. For example, here all these pins would carry the multiplier 1. And with K2 equal to wherever K2 is 0, so here and here again the multipliers would be 1. But in all the other cases, both N2 and K2 are non-zero, so the multipliers would be non-trivial. Is that correct? So the situation is like this. Let's draw the corresponding graph. Let's slightly reduce the size of these blocks now. We have to draw 3 of them. N2 equal to 0 block, N2 equal to 1 block, N2 equal to 2 block, and you have the indices N equal to 0, 3, 6, 9, 12 here, 1, 4, 7, 10, 13 here, 2, 5, 8, 11, 14 here, and you get the output pins. These are the X tildes here, and we have pin-wise multiplication by e raised to the power minus j 2 pi by 15 times N2 K2. Remember, the output pins are indexed by K2. So for example, here K2 would be 0, 1, 2, 3, 4 respectively. And similarly again 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So for example, this pin has N2 equal to 1, K2 equal to 2. And you multiply it by the, so it's just a point-wise multiplication or pin-wise multiplication. So you get 15 outputs again. And what you get here are the x double tildes after multiplication. And these are still indexed by N2 and K2. Now we come to the next step, and that is we need to take the n-point discrete Fourier transform of x double tilde n2 k2 for each k2. Now for each k2, and you need to take an n-point discrete Fourier transform. As expected, there are, you see, for each k2 means you must take corresponding pins from each box, and there are 5 such groups as expected. So you see, when there is an n-point discrete Fourier transform, there are going to be L such, which means 5 such. So you are going to have 5 discrete Fourier transforms, 5 3-point discrete Fourier transforms, and the 3 points involved in the discrete Fourier transforms are as follows. K2 equal to 0 will combine into one group. So we will take these 3 together and form one group. So we need a rearrangement. Then we will have to take K2 equal to 1. It's going to be confusing. So let's use different kinds of lines to denote each group. Up to here it was not too bad, but now we'll use a broken line. Now we'll use a broken and dotted line. And finally, we'll use a double line. So we have 5 of them. Here K2 is equal to 0, K2 is 1, K2 is 2, 3 and 4, and as expected it's a 3-point discrete Fourier transforms. Each of these are a 3-point discrete Fourier transform, and the output frequency variable is K1. So now, each of these pins, of course K1 takes the value 0, 1, 2 and that repeats 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. So now each of the frequency indices has been covered, each K2 and each K1 for every K2. So each of the frequency indices has been covered. Remember it was n times K1 plus K2. So of course, you know, when you fixed K2, you are jumping in steps of L here. So here you jumped in steps of 3, here you would jump in steps of 5. So the indices would be ordered as 0, 5, 10 on the first output, 1, 6, 11 on the second. So let's write that down. the output frequency indices are ordered as 0, 5, 10, 1, 6, 11, 2, 7, 12, 3, 8, 13, and finally 4, 9, 14. On the K2 equal to 0 box, K2 equal to 1, and so on up to K2 equal to 4. So you have a reordering of both the time and the frequency indices. Now of course it's not very difficult to reorder. So you can always reorder the indices by shuffling the outputs. That's not a problem. So if you want either the input to be fed in order or the output to be fed in order, all that you need to do is to put a shuffling step. So if you want what is called in-place computation of the input and the output, then what you do is feed xn, n going from whatever 0 to n minus 1. First have a shuffler, a reordering device. You shuffle them in such a way as is required for the first set of DFTs, the L point DFTs. Then you have L point DFTs. And M of them. Then you have a pointwise multiplication. Then you have a shuffle again. Let's continue on to the next page. From the point A, let's call this point A and continue from here on the next page. After shuffling, you have n point DFTs and L of them. And you get outputs. And here you get outputs, again not in order, so you need to shuffle these back again. And then you get the frequency points in order.
Can you skip a shuffler after the multiplier, point by multiplier?
So the question is, can you skip a shuffler after the pointwise multiplier? Yes, you can probably integrate the shuffle and the pointwise multiplication of. But you see, in a way, if you look at it carefully, you need to aggregate points together to form the groups for the DFTs. So whatever you want to call it, the point is that you need to take the correct set of points to take the M point and L point DFT. That's what I mean by shuffling. So if you want to keep everything in place, then you will need shuffling at appropriate points. So at the present moment, this is the easiest way to understand it, but later on one can perhaps remove one of the steps by merging. So I leave it to you to think of those possibilities. But this is a simplistic way of thinking about it. Of course, if you are not very particular about in-place computation, you can then reduce one of the shufflers also. Whatever it be, let us get a feel of what we have gained by this. So for example, if we take a 15-point discrete Fourier transform, what exactly have you gained? A 5-point DFT, you see the 5-point DFT at least at the moment cannot be reduced or simplified any further. So 5-point DFT would require essentially, if you take the multiplies, you have n equal to 0, 1, 2, 3, 4 and k equal to 0, 1, 2, 3, 4. So there are no multiplies for 0, but all the others have multiplies. So there are 4 cross 4, which is 16 multiplies. So 5-point DFT requires 16 multiplies and 5 into 4, that's 20 adds. Similarly, if you take a 3-point discrete Fourier transform, we can again set up the multiplication matrix n0, 1, 2, k0, 1, 2. Of course, this has no multiplication, but there are 2 cross 2, so 4 multiplies. And therefore, there are 4 multiplies and 3 multiplied by 2, that's 6 adds. Now, shuffling is not counted as an operation at all. It's just a placement of wires, or it's just taking wires from one point to the other notionally. So you're not counting shuffling as an operation. However, we do have 15, potentially 15 point-wise multipliers in this. So how many point-wise multipliers do we have? Well, again, n2 equal to 0 and k2 equal to 0 need to be excluded. So you see, 7 of them get out of the 15, you have had in general 15, out of which, if you take k2 equal to 0, that itself cuts out 5 of them, and therefore you have only 4 plus 4, 8, 7 are excluded. 8 are non-trivial. Is that correct? 8 are non-trivial. And therefore, in total, the computation that we have you see, you had, let's go back, you had 5 3-point DFTs. So multiplies, add, 5 into 4, 5 into 6. Then there are 8 multiplies in the point-wise step. So 5 3-point DFTs, point-wise multiplication, and 3 5-point DFTs. Let's look at what the 5-point DFTs cost us. 16 multiplies and 20 adds. 3 into 16 and 3 into 20. So we can add these. I leave it to you to complete the summation here. That doesn't require too much of advanced math. But directly, a 15-point DFT would require You see, again, construct the multiplication matrix 0 up to 14, 0 up to 14, and here the only thing that can be removed is the 0, nothing else. So 14 times 14, this many multiplies, plus 15 multiplied by 14 adds. So I leave it to you to compare the direct 15-point discrete Fourier transform in terms of computation and the fast Fourier transform by the 3 steps of decomposition, whose computation is here. And you will definitely see an advantage. I leave it to you to complete these numbers. Now we shall proceed tomorrow by looking in greater depths at how what we have done today relates to decimation in time and frequency and what variants are possible starting from what we have done today. Thank you.